Let's focus in on Storm A. We'll go further along in time out to 21 UTC. When the radar data is restored, you can see a high reflectivity core with our storm. In the IR imagery, we want to go to the time that we left off earlier at 2038. So I'll move that to the time we left off earlier. Note our overshooting top. Downwind of that, we observe a region of warmer brightness temperatures. If we go a little bit later in time, here's our overshooting top. Here's our region of warmer brightness temperatures, and we can pretty easily depict a enhanced V signature in there. And this enhanced V signature has a brightness temperature difference of between 14 and 17 degrees Celsius within a few minutes of this time. We'll resume our animation, and later I'll look at the visible imagery zoomed in to analyze for an above anvil cirrus plume in this location where we observe the warmer brightness temperatures. Let's look at some radar data. At the half-degree tilt, we're looking about 6,500 feet AGL for our storm. You can see here on the velocity data that there are indications of rotation before and after the radar outage. Let's look at the 1-minute imagery with an eye towards maximizing the information that we get from the imagery. So here's the overshooting top associated with Storm A. Here's the flanking line. And here's additional convection that's going along the dry line southwest of the storm. If we go a little bit later in time, focus on this region right here, and you'll observe inflow feeder clouds. Certainly around this particular time, you would identify these as inflow feeder clouds. They have these lines of low-level cumulus, and these are pointing towards the inflow region of the storm. They develop when you have an intense storm like this. So that's one of the storm scale signatures that we can see. If we go back a little bit further in time, I want you to focus in on the flanking line right here. And again, remember we saw indications of a rotating updraft by following that. And if we go a little bit later in time, one of the more subtle signatures that you can see is follow this cloud element right here. It originates along that flanking line, and as you follow this forward, it seems to get caught up in the inflow region, and by the time you get right here, it gets caught up in the inflow region of the storm, goes towards the storm. It's just another subtle indication of the intense inflow region that we have with this storm. And then if we go back to yet another subtle signature is on the backside of the storm. Recall that at times you might be able to see towering cumulus above an invigorated RFD, also known as flanking towers. So if we look just west of the flanking line in this region and go forward, you can see this area of clouds emanate out in this direction right here. And it's quite subtle, but those are the flanking towers that we see just west of the flanking line. I'll go back and forth so you can see those. An important point to make here is that these are quite a bit more subtle than the inflow feeder clouds that we see over here, but we do see them near the end of the loop. Another storm scale signature to watch for is the above anvil cirrus plume. It occurs in that region where we saw those warmer brightness temperatures downwind of the overshooting top. I circled in the area to watch because it's quite subtle. Look for smooth or more laminar looking cirrus that occur just downwind of the overshooting top. Watch for it within this circle, and I'll let this loop a few times so you can watch for it as it progresses along. And then I'll remove the annotation so you can see that a little bit more closely. So each of these storm scale signatures cumulatively should add to your confidence that we have a storm that's intensifying, and again, just being able to assess storm intensity trends by looking at the 1-minute visible imagery. When you analyze this loop of the 1-minute imagery in Storm Relative and in the GOES 16 projection, just ask yourself, are you able to identify the storm scale features with more clarity in this loop? In other words, can you more readily pick out the inflow feeder clouds that develop over here? Can you see the flanking line and the rotating updraft that goes up along that particular region and here along that flanking line, and also on the just to the west of that in this region, can you see the towering cumulus above the invigorated RFD that develops within that region with more clarity from this perspective? Also, don't be afraid to change color tables. The color table used here is a linear grayscale color table, while the previous loop used the default square root color table. The above anvil Cirrus plume shows up slightly darker in this color table, which may aid identification of that feature downwind of the overshooting top. Recall when we looked at the tracking meteogram output for Storm A, after about 2038 UTC, in the Earth Networks data down here in the bottom plot, you see a rapid decrease in the Earth Networks lightning data, and that did not occur in this middle plot with the GLM flash extent density. So that made us suspicious of the data. When we're looking at our plot, it's somewhat difficult to see after 2038 between these two. However, when you go to the zoomed out plot, this became much more readily apparent. If I stop the loop at a particular time and focus in on this lower left panel, you can see at one time the data is there, and then there's a drop off, and then it comes back, so you get this flickering effect. So being able to identify these type of unknown issues is key for data quality assessment, being able to identify it rapidly and allowing you to maintain your situational awareness, and in this particular case, having high confidence in your flash extent density and significantly decrease confidence in your Earth Networks data for this particular time period.